Has anybody thought about what the albedo changes of the Voyager spacecraft would be, and within the next 100 million years, it could very well pass through another system. Right. And because of its myriad flat surfaces in the rest, as it rotates, it will show rather dramatic albedo variation.
Right, so an alternative to having a very elongated object would be to have an object with a large albedo variation. Yeah, so, but again, it's very extreme. We haven't seen anything like that. And it appears that the color of the reddish color of this thing is very similar to asteroids that have been around for a while. However, the axis structure is quite anyway, so let's move on. We have 4 presentations today. The first one by Sownak Bose from the ITC. He will talk about the small-scale structure of cold dark matter. Then we'll hear from Brian Metzger, that will talk about accretion power flares from colliding memories as TD imposters. Then we'll hear from Michael McDonald, a physics at MIT, and he will talk about witnessing the stripping of hot halos as galaxies fall into clusters. And finally, we'll hear from Erica Nelson. She's visiting us from TD. Where is Erica? Over there. And she will talk about building galactic bulges. So.
Don't start the clock yet. Yeah. So today I wanted to talk about what I think is a very exciting project that I'm working on at the moment with this sort of illustrious company of people listed down there. And it is to do with what is titled the small-scale structure of cold dark matter. And to give you an impression of exactly what I mean by small-scale structure, I think a good place to start is by looking at the power spectrum of matter fluctuation. So what's shown here is the scale on the x-axis parameterized by the wave number, and on the y-axis is the dimensionless version of the power spectrum. And so what you can see here is essentially the picture that one expects from hierarchical structure formation, that is, you go to smaller and smaller scales, there's more power. And if you imagine, cold dark matter as being this sort of infinitely cold, collisionless particle, then you expect that this power sort of extends indefinitely to smaller scales. If you had a slightly different variant of the model of dark matter, something like warm dark matter, for example, these particles have some kind of thermal velocities when they're born. And what that does is that it introduces a characteristic scale in the theory where the power actually gets cut off. And for warm dark matter candidates, this occurs roughly around the scale of dwarf galaxies, so around halo masses of around 10 to the 8 or 10 to 9 solar masses. But it turns out that even for cold dark matter, if you consider an interesting candidate such as the 100 GeV neutralino, there is such a cutoff as well, because there is a finite velocity dispersion. But the difference to warm dark matter is that this is really pushed down to very, very small scales. So the scale is not dwarf galaxies, but many orders of magnitude below, at the scale of halos that have the mass of the Earth. Okay? And what happens around this free streaming scale is that the density perturbations are smoothed out, and this therefore suppresses the formation of structure. So you can visualize, therefore, what the mass spectrum for CDM would look like, where on the x-axis it goes from 10 to the minus 6 to 10 to the 15. So the smallest objects that form in a CDM 100 GeV neutralino universe is around the Earth mass, 10 to 15 for the rich clusters. And sort of state-of-the-art cosmological simulations have established a number of properties for the structure of dark matter and their abundance down to about 10 to the 6, and have established things like the mass function, the profiles of halos as following NFW profiles, and the so-called concentration mass relation. However, what you can see is that there's a big sort of region, about 12 orders of magnitude or so, which is really unexplored. And really the aim of this project is to do exactly that, to resolve and sample the entire mass function of cold dark matter, and specifically to look at this region where the properties of halos have been unexplored at redshift 0. And as I'll explain, this is a very, very challenging task. So I can imagine you're asking, why on earth would anyone care about this? So apart from the theoretical interest, one sort of observational thing that could be interesting is when you think of the annihilation of dark matter. So the expected flux that one gets if dark matter annihilates is essentially a convolution of two components, a sort of particle physics type component, which includes the cross-section of the dark matter, the mass of the particle, and so on. And there's another component which is essentially the integral of the density squared along the line of sight. And so obviously the clumpiness of the dark matter in the halo will add to some sort of contribution to this boost factor, as it's called. So if the cold dark matter is this 100 GeV neutralino whose annihilation we're trying to measure, theoretical simulations and predictions need to be able to tell you exactly what the clumpiness is like, what the internal structure of halos is like, all the way down to the smallest structures that can form at the present day. Okay, so it is that component that is what we're interested in. So the demands of this project is really, really quite challenging for two reasons. It's because A, we want to resolve these properties at redshift 0, so we can't just simulate a halo, get its predictions at a high redshift and extrapolate forward, because who knows if that's correct. But the second thing is that we want to resolve these tiny objects in their appropriate large-scale environment. So when people have tried to do these experiments before, what is done is you simulate a very, very tiny box in isolated conditions, and then you stop the simulation at higher redshift and you extrapolate the result over many redshifts. But we don't want to do that. We want to find what is the self-consistently modeled tidal field around the smallest objects that can form. So if you can imagine it as being, trying to resolve a Earth mass halo, so 10 to the minus 6 solar masses, inside a 500 megaparsec type volume. Now, if you think about it, doing something like that, if you want to resolve something of the mass of 10 to the minus 6 solar masses, with say 1 million particles only, that would require a particle mass of 10 to the minus 12 solar masses, right? Which, if you put that into a 500 megaparsec volume, that would require 10 to the 31 particles. So clearly you don't want to do that. So the technique you adopt is the following, which I try to very simplistically demonstrate here. So supposing we run a simulation where it's a 500 megaparsec volume that we've resolved at some resolution, and this is what the large-scale structure looks like. We say, okay, this is all well and good. Now let's focus on the region that we're interested in, say something in the middle, resolve that at higher resolution. So what we can do is pick a region of interest, and we increase the resolution in the middle, where we want the resolution, and coarsify the resolution outside. So you still sample the same density field overall, but you get better resolution where you need it. So doing that once helps you resolve something slightly better, but you can essentially keep repeating this procedure till you reach a sufficient resolution to resolve the underlying truth, right? Which is a very nice pun there, actually. And so the idea behind this nested zoom technique is that it brings resolution where you need it, whilst maintaining the same large-scale tidal field. So visually in our simulations, this is kind of what it looks like. So we have a simulation at some particular level. We choose a region of interest, which at the given resolution looks like that. And then we simulate that at a higher resolution. And that is still embedded in the same 500 megaparsec volume as its parent. And then we keep repeating that procedure. So you essentially get a large dynamic range in the same volume. So in the nomenclature of our simulations, it essentially progresses like this. So this is all inside a 500 megaparsec box. But each subsequent resolution that we work at resolves the high resolution region in smaller and smaller patches with smaller and smaller particles, to the extent that the final level that we want to go to has particle masses of around 10 to the minus 12 solar masses. So that's roughly the mass of the Earth's atmosphere, I think. And the size of the high resolution region will be approximately an astronomical unit, right? So that's an astronomical unit of high resolution particles embedded within a 500 megaparsec volume. So there's a tremendous dynamic range involved in these simulations. So let me show you some of the results that we have for the levels that we've done so far. So this is showing you the mass function of cold dark matter with the halo mass on the x-axis and the abundance of objects on the y-axis. So in the largest level that we have, we can resolve the biggest objects. So you can see things between 10 to 7 or so to 10 to the 13. Then with level 2, which is a zoom of level 1, we miss out on some of the larger objects, but we are able to resolve smaller things now. And then level 3, which is a zoom of level 2, we can build up to smaller masses going down to 10 to the 2. to level 4, which gives us down to about a solar mass, and level 5, which is as far as we've gone so far, about 0.1 solar masses or so. So this is now, I guess, for the first time, the mass function of cold dark matter resolved at redshift 0 across almost 15 orders of magnitude or so. Okay, and what's quite interesting is they all seem to lie on a fairly well-defined power law slope, which is what one expects from the particular cosmology this is looking at. So the other thing that I said was of interest was to look at what is the internal structure of these halos, right? So one way to parameterize this is in the form of something called the mass concentration relation. So there's a lot of ambiguity a lot of times regarding what the concentration actually is. So to demonstrate what I mean, so here's a halo that we've extracted from our simulation. So it has a mass of around 200 solar masses. You can define some kind of boundary to it, defined by its virial radius, and you compute its density profile in spherical shells, shown by these yellow circles. And the concentration is essentially obtained by fitting some kind of analytic form, such as the NFW profile. And you extract a concentration. And then doing that for all the halos across the various levels we have so far, you can build this mass concentration relation over, again, around 15 orders of magnitude at redshift 0. And what's quite interesting is that previous studies that have tried to predict the annihilation signal for dark matter have essentially measured the mass concentration relation down to about 10 to the 7 or so, and then extrapolated down the remaining 19 orders of magnitude, or whatever it is, right? And that power law slope actually, oh my goodness, that power law slope actually extends really far, ends up being a lot higher than what is actually predicted by these simulations that have self-consistently modeled it. So the relation is actually a lot flatter than what you see. And that will have a big impact on the boost factors that one measures. Okay, so in the last 30 seconds, the other interesting thing that one could look at is very much a theoretical pursuit, which is to understand whether or not the density profiles of dark matter are truly universal. So since childbirth, everyone is told that halos are described by NFW profiles, but some authors have shown that if you go to the free streaming scale, this is actually no longer true, and in fact, the slopes become power laws, described by a 1.5 slope. However, there are very special conditions that these simulations have been run in, specifically that they've stopped at high redshift and not modeled the large-scale environment. So who knows if this is actually the right answer or not. And because both the F and W of the profile are involved in this project, trying to establish whether or not this is truly the right answer or not is therefore of fundamental interest. And that's where I'd like to stop. Thank you. Right.
In those simulations, did you evolve the transfer function with some particular models of the dark matter?
Yeah, so we basically assumed that it was a neutralino of a 100 GeV particle, and then you have to assume some kind of decoupling temperature, which basically results in determining what the free streaming scale for that particle would be. So currently, the state where our simulations are, we are not yet at the scales that we can resolve the free streaming scale for this 100 GeV particle, but essentially the transfer function is there to represent the 100 GeV neutralino particle. And then eventually when we get to the sufficient resolution, that's where we'll start resolving the structures relevant to it.
So you said that you need to simulate this at redshift 0 because you're not sure, or we don't know if halos look similar at high redshift now. So can you comment on this in light of the simulations you just ran?
Yeah, well, so one comparison one can do, for example, is by so the famous examples of simulations that have been run till high redshift and stopped there is one by Ishiyama et al. And one by Diamond and Underhalden. And essentially what they do is that you simulated the halo and it stopped at redshift 30, because what happens is that the boxes that they simulate are so small that you can't go to low redshift, because then the nonlinearities that you don't have are basically the dominant fluctuations of the scale of the box. So you stop the simulations there, and then it's extrapolated forward with some kind of model for the redshift evolution of the concentrations. Now, a lot of these things are based on fairly old simulations. So the ones that those papers look at is based on the Bullock 2001 evolution model. And in some of the tests that we've done, where we look at what is the actual redshift 0 concentrations of, say, 100 solar mass object versus what you get if you were to stop a simulation in a small periodic box and evolve it forward in redshift, you actually get a fairly, a sizable difference in what the concentrations look like. And where it'll be more interesting is actually when you get to the free streaming scale, because it is at that scale where you don't actually know what you're missing out on by actually not having the large-scale tidal field. Okay, so because that will change exactly what the shape of your high-resolution region is looking like. It will change the merger history of the halo, and therefore it can have an impact on exactly what slopes you're inferring for the density profile, and therefore what concentrations you would actually measure out of it.
So is it obvious in this nesting scheme that the regions you're looking at in high resolution are not affected by substructure, that you're not resolving outside the boundary of that region? So actually that's a very interesting point. So we spent a lot of time actually trying to determine exactly how this nesting scheme should be done. So what turns out to be the case is that if you don't have a very smooth transition between the masses that is sampling the various high resolution region and then the low resolution boundaries, you can actually get errors in the force that are quite sizable. And therefore, if you try to look at objects that you have formed in, say, a level 3 simulation, they will not look similar to what it was like in level 2 because you have not adequately sampled the intermediate scales. So there is a lot of numerics involved in trying to figure out exactly what the sampling of masses, the hierarchy of masses should be. And you can do these kinds of, convergence tests and, looking at what are the sort of errors that one gets on the force calculation to see exactly what is the effect of not sampling these things correctly.
Of course, the interesting point is that for the baryons, there is the Gibbs
Yes.
length or mass below which you don't have fluctuations. So in principle, in the very first galaxies, the clumps of dark matter would see fluctuations in the gas and trigger star formation.
Right.
So that are quite important, and that was never simulated.
Exactly. So actually, the slide I didn't show, one of the points that we want to look at is essentially what happens when you put baryons into this. And what's quite interesting about this is that you don't really need a very sophisticated model for how baryonic physics works in this, because you don't really care about things like feedback and all that kind of stuff in the beginning. You just need essentially what happens with a smooth baryonic field and how that affects the initial density field, and you can model things as a result of it. So these are all these kinds of things, I think things that have not really been studied in any great detail, so it would be worthwhile to look at it.
We look forward to hearing about them from you in the future.
In the future, yes, indeed.
Thank you very much.
Okay, thank you.
Okay, to talk about something which I'll admit is rather speculative, but maybe a bit fun. Okay, do you have a laser pointer here? Okay. Oh, it works or no? Okay. Okay, so I'm going to talk about some work I did with Nick Stone, who I think everyone knows since he was a graduate student here, on accretion-powered flares from colliding EMRIs as TDE imposters. So the idea is that we see these flares from galactic nuclei. We think they're TDEs, but is there anything else that could be masquerading as TDEs, producing sudden accretion events on the supermassive black holes? And so what we're going to argue is that one thing we should possibly be thinking about are EMRIs of main sequence stars that are overflowing their Roche bond to the supermassive black hole. And if you have two consecutive EMRIs, they may actually interact with each other physically, colliding and producing bursts of gas. Sounds like a lot.
You may want to explain what EMRI is.
Sorry. EMRIs are extreme mass ratio in spirals, so I'll talk to that in a second. So these are stars that come in not on highly eccentric orbits, but on relatively circular orbits, which enable them to circularize around the black hole. So I think most people have heard of what a tidal disruption event is since James is here, but essentially you have a star that's on a very highly eccentric orbit that enters the tidal sphere of the black hole. It's torn apart, and then this forms an accretion disk, which feeds the black hole, producing a transient flare of emission. These are expected to happen roughly every 10,000 or 100,000 years in a galaxy like our own. Oops, I crashed the... Oh, sorry. In a galaxy like our own. And this is sort of... And we see these flares in galactic nuclei as X-ray flares, often as optical flares. But one of the mysteries, at least associated with the optical TDs, is that they're surprisingly wimpy. If you just calculate, their radiate energy doing a bolometric correction, it's typically less than 10 to the 50 or 51 ergs. So if these things were accreting as thin accretion disks, 10% rate of efficiency, which we don't necessarily know is true, but if they were, that imply that a fairly little amount of mass is accreted, maybe less than 100th or even a thousandth of a solar mass in some cases. Whereas we expect about half of the stars should actually be fed into the black hole in these systems. Now, there are other explanations for why these could be wimpy, but one thing is maybe these are just not as accretion events which are as massive as a single star. So another way we might get some interesting interaction in galactic nuclei are these extreme mass ratio in spirals. So instead of having a star which enters on a highly eccentric orbit and is disrupted, if you have a star which comes on a lower eccentricity orbit, it actually has a chance to circularize and feed mass into the black hole that way. Still, what we call EMRIs that are kicked in through two-body interactions still tend to be fairly high eccentricity and probably are disrupted. But there is this idea for creating lower eccentricity EMRIs from tidally detached binaries. So you have a binary that comes in, one star interacts with the black hole, one star is ejected as a hypervelocity star, and the other star gets placed into a more elliptical orbit, which then over time circularizes through gravitational waves. And by the time it enters the tidal sphere, it can be quite low eccentricity, that it may actually not be disrupted, but circularize. I'll discuss that in a second, and feed mass onto the black hole slowly. But the rates of these are probably 1,000 times lower than the tidal disruption event rate. I'll get back to in a second why that may not be so relevant. So this star is basically now feeding gas slowly onto the supermassive black hole. So it's actually a system very similar to a CV system. Okay, so this is the semi-major axis of the star when it begins overflowing its Roche lobe as a function of time, since it overflows its Roche lobe. And so as the star is consumed, usually what happens is sometimes for more massive stars it will actually expand briefly and then the orbit will shrink. So we're talking about scales of a few astronomical units. Then once it goes down to about a tenth of a solar mass, its equation of state changes. It reaches a period minimum, also like CVs, and then backs back out to a longer orbital period. But the point is that you can have, in principle, a supermassive black hole which is accreting from one of these stars for millions of years. And so the idea here is that the interval between these EMRI events, which as I mentioned, maybe once every 10 million years, is actually similar to the evolution time scale over which a given EMRI transfers mass to the black hole. So you might have an interaction between two of them. Say I have a low mass star which comes in and starts feeding gas onto the black hole, reaches a period minimum and starts going out. And then a more massive one comes in and starts feeding gas. And actually at some point their orbits cross and they may strongly interact. Okay. And so this is what I basically just said in words. And so you might say, well, okay, they're probably in different orbital planes. That actually doesn't matter because their orbits, they're in circular orbits, so their planes necessarily cross at some point, and they're not in quite the same semi-major axis, so the orbits have different phases. And so there's actually the number of orbits that it takes for their phases to align and the two stars to actually cross each other is actually smaller than the number of orbits it takes the more massive one to pass the less massive one radially. So basically what we concluded from this is if you did have two consecutive EMRIs, an actual direct physical collision between them is inevitable. And by comparing these two, you can actually figure out the characteristics of that collision. So typically, depending on the mass of the black hole, the less massive star here, which is they both have the same density since they're both overflowing the Roche lobe onto the black hole. But the less massive one is actually physically denser, and it will collide with, say, the more massive one with an impact parameter that might be a few percent of its radius typically. But on these scales, the velocities, orbital velocities, are enormous. They're like fractions of the speed of light. So even that single collision will produce a shock heating of the lower density star, and inject a bunch of energy into it. And you can estimate the maximum amount of mass which is ejected by this process by just equating the amount of energy dissipated by that collision to the binding energy of the more massive star. And it can vary, so it can be quite small. It turns out if you have lower mass, supermassive black holes, 10 to the 6, it could be a small amount of mass is ejected. But it could be, much larger. The impacts tend to be higher impact parameter, deeper impacts for more massive black holes. Okay, so the net effect is that these two stars collide, strip off some mass, and you create a temporary accretion disk around the black hole. And unlike a TD, it's actually already fairly circularized, and so you could produce a flare of emission this way. Okay. And so you might say, well, why do I care? Since EMRIs, as I mentioned at the beginning, these types of EMRIs are probably 1,000 times less common than normal TDEs. Well, the idea is that actually a single one of these two binaries could actually do this multiple times. So the speculation is that if you do actually, the mass is stripped off from this collision, if that angular momentum actually ends up going back into the angular momentum of the outer binary, you can ask me why that might be the case after, it will actually cause its orbit to expand, okay, because it's losing mass, but it's keeping that angular momentum. And so now it's far enough away from the other star that they're no longer interacting. But then after some additional amount of time, gravitational waves will bring this one in again, and they will collide a second time, lose mass, back out, collide a third time, like this. And so, you sort of death by 1,000 cuts, you'll destroy one of the stars or both of the stars, and so you can potentially get many flares from the same pair of EMRIs, potentially. This is just the estimate, depending. For a more massive black hole, the single collision tends to destroy them. For the less massive ones, it tends to be a grazing nick, which produces possibly many low luminosity flares. So you might say, well, how could I distinguish this from a normal TD? Well, you probably know. In a normal TD, the mass feeding onto the black hole is dominated by the fallback rate, which decays as t to the minus 5/3. In these cases, you're forming a disk, and the accretion rate is probably more controlled by the viscous spreading of the disk, which tends to produce a power law decay, which is shallower than t to the minus 5/3. It's also possible if you're feeding the angular momentum of the disk back into the binary, you can show that if the disk doesn't have a chance to viscously spread, then its accretion rate will drop actually as an exponential in time. And there are some TDEs where people have claimed to fit the light curves as exponentials, although I think the data is still a bit iffy on whether you could also fit them as power laws. It's also possible that this would predict periodic TDEs because you could get multiple collisions from the same galactic nucleus. In general, we find that the time scale between the collisions is quite long, but you can play with the parameters, and you might be able to get time scales as short as decades or centuries. And there are some potential repeating TDEs that people have discussed, IC 3599, where people claim that there have been multiple flares from the same nucleus. Okay, I'm not purporting this too strongly. I'm just saying that this is the kind of thing we could look for. And we also know that TDEs tend to their rate, for some reason we don't understand, tends to be enhanced in post-starburst galaxies. And much like that, we do expect that many of these EMRIs are actually enter the loss cone of the supermassive black hole, these binaries that create these EMRIs through interactions with massive perturbers like molecular clouds and other things that might be more prevalent in post-starburst galaxies. So there are reasons why you might expect these to be enhanced in post-starburst galaxies. And we do predict some black hole mass dependence of these guys. So we expect that lower mass black holes will, and if this scenario is correct, produce a larger number of flares, but they will be dimmer, whereas more massive ones will produce a single one. So that's basically what I had to say. Just to summarize, actual TDE flares tend to be a bit wimpier than we'd expect. So there's, it's useful to think about what else could be going on in galactic nuclei that feeds periodic mass onto the black hole. One idea is if we have these stars that come in on almost circular orbits and feed mass slowly onto the black hole, which were discussed previously by people like Jane Dye and Roger Blanford, you could have another one come in and there could be collisions between the stars. And this could produce some interesting dynamics. I should tell you, this is just an idea at this point. We have to do, more work to understand the stability of these colliding stars. How much mass do they lose from these collisions, etc. So I'll finish there. Thanks. Right. On larger scales, yes. I know you've worked on this with Schmel. Yeah, that's what I'd say. There are collisions that happen on a bit larger scales, but they don't feed gas to the black hole fast enough to produce a very luminous flare. That would be my point.
So, I think giants have really been the focus of a lot of these, like James work and stuff. You seem to focus on main sequence stars. Is there a reason why you focus on main sequence as opposed to, say, giant?
Well, giant stars would overflow, I guess, at much larger radii. So, if I get these main sequence stars, I get them down there deep in the potential where, well, where a collision will dump in some gas, at a high rate. So I haven't thought about, and also I don't know, I haven't thought of, I guess in just general, main sequence stars are more common than giants, so.
The giants have a much bigger
Cross-section for what? For collisions, yes. So I have,
Yeah, so I imagine another way to bring two stars in on nearby circular orbits is there's an existing accretion disk around the black hole. And you can have migration tracks in these disks. Have you considered what this would look like in the presence of a pre-existing disk?
No, it's fascinating. If you had an AGN disk that was bringing in a star and then the star started overflowing its Roche lobe, like inside the disk, I have no idea. That's fascinating. I don't know. I don't know if the existing inside one of these disks would somehow destabilize the orbit. I mean, that's sort of one of the concerns here is how these do tend to be fair, stable mass transfer situations, but you'd worry in that environment that the idea here is if it's an isolation, this disk has a decent chance of feeding its angular momentum, or at least part of its angular momentum, back into the binary, which keeps it stable. But if it was inside an AGN disk, I don't know. Okay, I see what you're saying. Without them overflowing, Roche lobe. Yeah, I think you can get. I think there are multiple ways to get collisions. I guess what I'm focusing on here are collisions that happen really close to the black hole. So it's not really the collision we're seeing. It's that gas from the collision then accreting onto the black hole. Yeah.
Yeah, to come back to something that I think James said a little earlier about giants.
Yeah.
I think that's an intriguing thing. As Avi pointed out, the rate is high.
Yeah.
There was one thing in the past where we were thinking more about tidal disruptions, because it turns out that in the only two galaxies that we can actually resolve the center at the level of an arcsecond with Chandra, there is actually a very soft X-ray source near the center of the galaxy that could be a stripped core of a giant. So that was very suggestive that maybe something was going on. Now, alternatively, in the EMRI model that you're looking at, if the stripped core manages to stay in orbit, then it's a fantastic, I don't know whether you call it the target or sort of the bullet that hits the other star. And there is some work on this by Mike Shara, sort of what happens when a compact object goes through a star.
Right.
So that actually may provide some nice fodder for your calculations,
Okay.
which are very nice.
Thanks. Yeah, I mean, people have talked. Yeah, and I know that these ideas of collisions with giants have been discussed as ways to solve the the missing giant issue in the Galactic Center too, and most of that's happening on a bit larger scales. But if there was ways through these collisions to actually drive more stars down to the black hole, that would be very interesting. Okay.
Good. Okay, so I'm going to just very quickly talk about some research a student of mine has done. I'm Mike McDonald, by the way, on looking at the stripping of hot halos as galaxies fall into galaxy clusters. So just very, very brief background. We all know that galaxies and clusters are typically red and dead. They probably experience quenching sort of more effectively or more efficiently than in the field environment. And so as you go to higher environmental density, the colors of galaxies primarily shift from blue to red. And so cluster galaxies are by and large quenched, and they probably quenched very early. And so we're not entirely sure how this quenching occurs. There's a lot of different environmentally driven quenching mechanisms. For example, galaxy-galaxy mergers. Two blue galaxies, when they smash together, will typically make a red galaxy, and so this can drive the transition from blue to red. But galaxy-galaxy mergers are probably not prevalent in clusters because the relative galaxy velocities are quite high in clusters. So this is probably not driving that relationship that you saw in the previous slide, but it's a beautiful picture, so we'll just pause for a second. Another option is ramp pressure stripping, right? So as a gas-rich galaxy falls into a cluster, the atomic gas, the molecular gas, the warm ionized gas will all, could all strip as the galaxy falls in towards the center of the cluster, and it's experiencing ramp pressure against the hot intercluster medium, which fills the whole cluster environment, in which I'll talk about for an hour this afternoon. So here's a picture of what we call the jellyfish galaxies. These are galaxies that are falling in, and the hot ICM is stripping the molecular gas and stripping the atomic gas from the galaxy, which should very rapidly quench star formation, because you're taking away the fuel for star formation, and so there's just nothing left to make stars out of. And so this is a rapid timescale process. Quenching should happen on order a billion years. This is this is cold ramp pressure stripping. You can also have hot ramp pressure stripping, and the idea is that galaxies like our Milky Way have their own hot halo. This halo will replenish gas in the disk as the disk runs out of fuel, and so star formation can proceed much longer than the timescale to exhaust the cold gas reservoir in our galaxy. The hot halo around a galaxy is very tenuous, and so as you fall into a cluster which has a very dense intercluster medium or a dense plasma, the hot halo will very easily strip compared to the molecular gas and the atomic gas in the disk. So here's a Chandra image of a galaxy falling into a cluster, and you see the hot halo in blue that's being stripped away. And this is a beautiful picture, but it's sort of anecdotal. We don't have a sort of systematic search for this type of event in the cluster environment, and the reason for that is because it's very hard to see this stripping against the cluster environment, right? Because the ICM, the intercluster medium, is very, very bright in X-rays, and we're looking for a very, very faint stripping tail. And so, these are three options for what's driving the morphological evolution, or the morphological evolution. People seem to think that ramp pressure stripping of the hot gas is the dominant mechanism, primarily because of indirect signatures, right? So there's elevated metals in cluster galaxies, which you sort of only get if star formation has been proceeding for a very long time. So it doesn't look like it was quenched very rapidly. The stellar populations seem to agree more with a slow decline in star formation rather than a rapid decline. But these are sort of indirect evidences for this ramp pressure stripping of the hot halo. So we set out to actually directly look for stripping of the hot halo, so we can say, this is a thing that definitely happens, even though we're pretty sure it happens, but obviously you'd like to just see it. And so that's what we did. We went to a Bell 1795, which is a very nearby cluster, redshift 0.0625, I think. And so this is a Chandra image, a press image of Bell 1795. And this is, the inner part of the cluster. And the reason we picked 1795, this is my very bad picture of Chandra pointings that I just made literally a minute ago. The reason we picked this one is because Alexei Viklinin, who's here, maybe not here in the room, but here, in the building maybe, recently had a big Chandra program to image this cluster out past the virial radius with Chandra. And so there's a tremendous amount of data both in the center of the cluster, because Bell 1795 is also a calibration source for Chandra. So there's very good data in the inner part, and there's very good data in the outer part. And so we can actually look at galaxies outside the virial radius and inside the virial radius and sort of everywhere in between. And so that's what we did. We set out to look for evidence of stripping as galaxies cross the virial radius of a Bell 1795. It turns out that's really hard to do because there's a lot of other things that are X-ray bright, right? And so so the strategy here was to stack galaxies inside the virial radius and stack galaxies outside the virial radius and have two, really, really deep postage stamps, basically, of the average galaxy inside and outside. And so the average galaxy in both of those regimes has an AGN in the center, right? And so we had to, make a model for that. The tough part is that, these pointings are sort of pseudo-random, and so the galaxies fall in different parts of the field of view. And for Chandra, that means that they all have a different PSF. And so we had to simulate the PSF at the position of all the stacking positions, which luckily we can do because there's very great people here and elsewhere that make these packages for us. There's also going to be signatures from low mass and high mass X-ray binaries. So at the same time, we stacked Sloan data. We stacked Sloan I-band data as a proxy for the low mass X-ray binary, and we stacked Sloan U-band data as a proxy for the high mass X-ray binary. So these are the stacked Sloan images. They look like circular things because you're stacking a bunch of galaxies. And so the idea was we have these three models, our AGN profile, our low mass X-ray binary profile, and our high mass X-ray binary profile, and then we can scale each of these three just with one free parameter, basically. So we can fit the stacked X-ray signal with a model that only has three free parameters, which is the normalization of each of these things. But the shape of the X-ray binary profile ought to look like the shape of the stellar population, if nature's kind. All right, so this is the results here. So the top panels are the stacked X-ray profiles. On the left is the interior to R500 stack. On the right is exterior to R500. The red and green are what we call our baseline models, which is just AGN plus low and high mass X-ray binaries plus a uniform background from the cluster emission, which is extremely bright. And then that's it. So just these four components. We tie, so my bullets here have meaning. The little squiggly thing means we tie the normalizations of the X-ray binaries interior and exterior to R500. Right, X-ray binaries shouldn't be brighter per unit I-band luminosity when they cross the virial radius. That would be really, annoying. So we assume that they're tied. And so the point is, without getting into too much detail, the residual on the left is basically flat. So there's no evidence that we need another component for galaxies inside of the virial radius. Outside of the virial radius, there's this spatially extended residual that looks like we require an additional component to our fit beyond just X-ray binaries, AGN, and cluster emission. And so we fit that. And so here's the next plot. And so the blue model now is if we have AGN, low mass X-ray binary, high mass X-ray binary, background, that's 4 free parameters, and then we add a beta function. So it's just a height and a fall-off radius. And that does a pretty good job. So the blue now is the residuals when we add an extended component. And the blue line goes through the data very nicely. And so the idea here, so a very simple idea, is that if we stack on galaxies interior to R500, the profile is the X-ray profile of the stacked image is very well described by just X-ray binaries. Really, you don't even need the AGN, actually, and a background. When you get outside R500, suddenly you need an AGN component. So AGN are more prevalent outside the virial radius, which is a side result. But more importantly, you need an extended halo component in the X-ray. So we can compare that to what other people have measured. All these blue and red points are they're pointed observations for the most part, and they're kind of all over the local universe. The point is these two green points, we have two stacks at the same stellar mass, basically, with about 2 orders of magnitude difference in X-ray luminosity. And this is the halo component only, right? So this is the residual above AGN, X-ray binary, and background. And so galaxies in the cluster outskirts have 2 orders of magnitude more X-ray luminosity in this fluffy halo component than galaxies interior to the virial radius. And that's kind of cute, I think. What I didn't show, because I thought I'd talk slower, I guess, is that, if we do the full PDF, we rule out that these are from the same distribution at, the greater than 5 sigma level. So this is a very robust detection. We also see that the AGN are much, much brighter exterior to the virial radius, which confirms, previous work by folks at Stanford. And I'll just put this here. The cool thing is that this is essentially a 3 megasecond image of a galaxy inside the cluster and a 3 megasecond image of the galaxy outside the cluster by stacking all this data, right? So we have very, very good statistics on our average galaxy, which let us do this type of observation, which is very complementary to something like this one on the right. So I'll stop there. Sure.
But it allows gas to escape more easily, the fact that we have less dark matter in the heavens when they enter.
Right.
So that helps also. And it would be interesting to perhaps compare the scale to the truncated halos to the scale that you get.
Right. I mean, I was a bit surprised to see really anything, even at R500. I would have thought the stripping happened even earlier, like, 2 or 3 times R500. But apparently there's still galaxies with gas at R500, despite how dense the ICM is there. So.
So the distances you have are in two-dimensional integration of planes of sky. How do you marginalize the fact that you don't have the three-dimensional distance?
Right. So you'll see here that we only use 61 members. So these are all spectroscopic members. We could have used hundreds if we went with PhotoZs, but then we're just going to smear out. We expect basically everything that's not in the cluster to have a halo, and so we're going to really mess up our signal if we add things that we're not too sure about. So these are spectroscopically confirmed cluster members. So to the extent that one can say that they're in the cluster, we can say they're in the cluster.
But I guess I was just asking the distances there's a bit of an uncertainty to it, right?
They're all the same distance. They're all in the same cluster, if that's what you mean. Okay, sure. So if I understand what you're saying, this is a minimum difference between the two, basically. So things that are what we call in the cluster could be outside the cluster, but things that we call outside the cluster cannot be inside the cluster, right? So our bin on the bottom there, galaxies in the cluster core, is going to be boosted high by the fact that some of them might be outside the core along the line of sight. So that point's really an upper limit. The point at the top is relatively solid because projection can't work that way. Yeah.
Is there any, I don't know if you have the resolution to tell, is there any way to tell if the fluffiness is associated with the AGN component? Because you see both of them, don't you, in the outside R500?
Right, so they're very different scales. So if you look at this, I guess, the fluffiness is, well, it's hard, I guess it's tough. It's on roughly 10 kiloparsec scales. The AGN is basically 1 pixel on this, like it's, very, with 1 arc second. So they're very different. Is that what you mean? I mean, so they both happen outside the cluster, but probably for 2 sort of very different reasons, I think.
Here we go. Now I'm just nervous about being too loud. Just like flag me if I'm shouting too loud at you and like making you feel deaf. So I'm Erica Nelson. I'm delighted to be here today talking to you. As Avi said, I'm visiting from MPE in Munich. I'm actually technically a visiting scholar here, although my physical person has not really like been in the building. But I feel like I'm here in spirit like 46 to 85 times a day when I check my inbox. Did you guys know you get a ton of email? Like just an astonishing quantity of email. But it's very exciting. I mean, it's an exciting place. There's lots going on. I'm hoping to be here more in the new year. And so if you're interested in things Galaxy or James Webb, I'm always interested in collaborating. So the James Webb Space Telescope, that is. Okay, so yeah, you probably knew that. You knew I wasn't talking about like the NASA administrator. Okay, so I'm here today to talk to you about the structural assembly of galaxies. And so I want to start by giving like a brief overview of where this field is right now, and then briefly talk about how some of my work has given us insight into the physical processes that drive galaxy evolution, and then finish by just briefly telling you where I think this field is going in the next couple of years. And obviously all these things will be brief because I have about 7 minutes starting now. Okay. 8. Oh God, I was really hoping I wasn't right about that. Okay, so one of the fundamental questions that we are trying to answer in understanding galaxy formation and evolution is how did galaxies construct their stellar mass? How, over the course of cosmic history, did galaxies assemble the billions of stars that make them up? And one of the key ways that we can understand the physical processes driving the evolution of galaxies is by looking at the structures in galaxies. And so, of course, the primary structural building blocks of galaxies are their bulges and their disks. And so I want to talk a little today about what we know from the observational side about how the bulges and disks of galaxies form and what kind of constraints that puts on the physical processes that drive galaxy evolution. The general physical picture is something like galaxies accrete their gas from the cosmic web at a rate that's driven by the mass of their dark matter halo. That gas settles into the disks of galaxies and forms stars with a radial distribution set by the angular momentum distribution of the halo and affected by feedback processes. And then in a lambda CDM cosmology, galaxies undergo mergers. They're built up from smaller systems, and due to loss of angular momentum, due to dynamical friction, matter amasses at the centers of galaxies. And so, we've heard earlier today, and I think a lot of us are aware of how difficult it is to nail down the details of these processes in simulations. And this is also very hard to do in observations. And kind of the fundamental reason, of course, is that galaxies evolve over billions of years, and so we can't actually watch galaxies build up. We can't watch these physical processes take place. But the other reason is that most of the star formation in galaxies happened in the very distant past. And since the stars emit a lot of their light in the rest frame optical, we really need to be able to probe the rest frame optical in galaxies to see how they're building their stellar mass. And at these high redshifts, that is redshifted to the infrared, and infrared detectors have not been great. But there's been significant improvements in the observational landscape over the last several years. In particular, with the installation of the Wide Field Camera 3 on the Hubble Space Telescope in 2009, this really allowed us to resolve the stellar mass content of galaxies across most of the history of the universe. So out to near the peak of the cosmic star formation history, we can see where stars lived in galaxies. And what we saw is that as galaxies build up their stellar mass, they get larger in size, and they get increasingly bulge dominated. And so we can see that both in their images and their surface brightness profiles. And the question that we want to answer is, how does that happen? So we know structurally how galaxies are evolving, but we want to know how. And so, in particular, there's been a lot of different, there's a lot of discussion and a lot of debate about how the bulges of galaxies form. This has been particularly contentious over the last several years. As we've accumulated more data, we've also accumulated more theories of how the dense centers of galaxies form. So I'm not going to linger on this because I know I have about 2 minutes left at this point, but I keep hoping it'll be like, oh, still 7, that's magical. So we think these, there's this huge range of processes that have been proposed. These things can form in mergers or compaction, as one of our colleagues in the room can tell us about. The misaligned accretion, clump migration, secular evolution, parallel tracks, which is kind of an empirical description. So there's this, we've proliferated in the number of ways that we think we can form the dense centers of galaxies. But we can't actually watch these processes unfold in actual evolving galaxies. And so we need to be able to place, in order to understand this in the observed universe, we need to place empirical constraints on how this might happen. Of course, we can watch all these things play out in theory land, but who knows if that's right unless we can observe it in the universe. And so I think a particularly powerful methodology in order to place observational constraints on the structural assembly of galaxies is if we can map both their stars and their star formation across cosmic time. That allows us to determine whether whether these different structural components formed via ex situ processes or in situ processes, and hence place constraints on which of these physical drivers are responsible. So as part of my previous work, I developed a method to map the distribution of star formation in galaxies at early cosmic times. And that meant we could go from samples of about 60 galaxies to samples of about 3,200 galaxies, which was really a game changer in terms of our ability to, in a systematic way, assess the structural properties of galaxy growth. So I think I'm just going to skip this, but basically say that one of the key results that we found, which a number of other people found as well, is that it seemed that most of the star formation in most galaxies occurred in galactic disks. And this poses a couple problems, because this is these early cosmic times based on galactic archaeology and look-back studies are when we think the bulges of galaxies like the Milky Way and Andromeda built. And so, but we're not seeing this star formation building these bulges. And so the question is, how do you build these bulges? Do you have to, for instance, do you have to invoke do you form all these stars and disks and then in some way drive them into the centers of galaxies via, stellar migration or secular evolution, or how do you build these bulges? And so I think the reason that we're not seeing the building of bulges in our typical ways of probing star formation is dust. I know this is like deep in observer land, and so I apologize. I know you're theorists and you're like, dust, I really don't care. But it's important because in massive galaxies, over 90% of the star formation is dust obscured. And so if you're trying to figure out where these galaxies are growing, it's essential to know where the dust obscured star formation is happening. And you can't necessarily just assume that it's happening in the same places as the unobscured star formation. So the takeaway here is that in massive galaxies, we see a lot of dust-obscured star formation. And if we look at the Balmer decrement, which is observer way of talking about where dust-obscured star formation is happening, we see that in the centers of massive galaxies, there's significant dust-obscured star formation, suggesting that we may be missing bulge formation, which is happening through dust-obscured star formation. The key prediction of this is that this dust-obscured star formation should be absorbed and re-radiated in infrared wavelengths. And so to test this, I recently led a program to do millimeter interferometry on the progenitor, what we think is the progenitor of a galaxy like Andromeda, at a redshift of 1.25. So these are the unobscured tracers of star formation. So this is UV emission and H-alpha emission. And as you can see, there's this kind of ring of star formation in both the UV and H-alpha emission, which if this were representative of all the star formation, it would suggest that this galaxy is essentially, working on it, is essentially quenched in the center. However, if you look at the dust continuum emission, this hole, this ring is filled in by dust continuum emission. And so there is significant dust-obscured bulge growth in this galaxy. And since I am out of time, I'll just skip this, but the point is that we can use these types of observations to place empirical constraints on how galaxies grow, and what this is showing is essentially we can account for the structural buildup of galaxies if this galaxy is representative simply by star formation. We don't need to invoke other processes like mergers or compaction in order to redistribute stars after they're formed. So just to conclude briefly, looking ahead, I think this is a really exciting time for studies of galaxy formation and evolution. The negative K correction and the resolution and sensitivity of ALMA. And for me, I'm particularly excited about the launch of the James Webb Space Telescope in early 2019. This is like my area of observational expertise, and it's going to be just a remarkable instrument, as well as the increasing resolution of the cosmological hydrodynamical simulations. I think for the first time in the next 10 years, we're really going to be able to tell the narrative of how the structure of galaxies emerged. And I think this is a really exciting time to study galaxies. Thank you. They're pretty bad, I would say. Yeah, so we're working on it. I mean, I think it appears at this point that the contribution of dust-obscured star formation to the cosmic star formation history kind of peaks also at the peak of the cosmic star formation history at about redshift 2. Beyond that, our constraints are quite poor. But I think they're even, and they're better at the peak of the cosmic star formation history and after that. But, we still struggle from lack of sensitivity in these infrared, for these infrared observations that we use. So I think there's still a lot of, and as Joel can tell you, there's still a lot of room for improvement, especially in terms of how we interpret those observations also.
Looks like everything you described was very clear.
Clearly. Thank you.